Hey everybody, Chris from FlipMath here, and I'm going to take you through today's lesson, which is part of the trigonometry course, and I'm called it Graphs and Equations. It's part of the from the Mathematical Methods course, and it's part of the Pure Maths Algebra, part of that. Okay, our objectives today. We're going to draw the trigonometric graphs for sine, cos, and tan, solve equations involving sine, cos, and tan with more than one solution, possibly, and we'll come back to that in a second. And we're going to solve problems for 1 theta and for k. I've said k theta, but 2, 3, 3 theta, etc. So we'll have covered, what sine, cos, and tan are, bin ratios. If you haven't, go back to the previous videos. And in this case, I'm going to show you exactly. Well, you're going to learn a bit more about them. Kind of broaden your horizons about what you think about it. So trigonometry as a thing, as a topic, is a living, breathing animal, not like a tiger or a giraffe, but more like a bacteria, if you want. The trigonometric ratios, sine, cos, and tan, aren't just stagnant. They change and subsequently repeat over time. And again, we'll see this in a second. So we're going to recap. We're going to solve some simple trigonometric equations, and you might even have thought of these as equations, but they were. What you should know, well, this is the GCSE topic, so any of the kind of first lot of GCSE stuff you should know, or like the right angle triangle, sine, cos, and tan within a right angle triangle, something like that. So we've been looking at triangles for a few weeks. We've examined triangles of the right angled form and non-right angled, and our knowledge has progressed from GCSE to where we kind of are now. So if I asked you to solve the equation sine of theta equals 0.5, where theta is an unknown angle. So what values or what angles, when you take the sine of them, give you 0.5? So I'm really asking you for the angle for which the ratio of the opposite, the hypotenuse, which is the sine ratio, is 0.5. So when I divide the opposite by the hypotenuse. So in this case, that's an opposite over there, hypotenuse up there. And you would do this by getting your calculator and doing inverse sine, or sine to the minus 1 of 0.5. And if you do that, and you can check it, you should get 30 degrees. But it's not the only solution. Okay, and we'll show you why. This is a trigonometric graph paper, so to speak. So along the x-axis, or what we call the x-axis, we have degrees going up in 45 degrees, so 0, 45, 90, 135, 180. So they're going up in 45 degree steps. And also in the other direction, minus 45, minus 90, minus 135, and minus 180. And on the y-axis, we're going to get the value, the amplitude, the magnitude, if you want, or whatever way you want to think of it, right? So the degrees go along here, or the value, or the amount, or whatever you're going to say, the ratio, if you want as well. So we're going to calculate the values of certain angles and plot them, right? Just like you would any other graph. So get your calculator to hand, and let's do the sine graph. So calculator might look a little like this. And what we're going to do is we're going to do sine, and we're going to do naught. Now, putting in brackets isn't 100% necessary, but in these calculators, they will open brackets for you, and they close them. So we put sine, 0, hit the equals button, and you should get 0. Your calculator is correct. That's not an error. We're going to plot 0 degrees, which is this bit in here, with 0 as our value along here. So our first value is going to go slap bang at 0, 0. If I repeat the thing, and we'll go up in 45 degrees, so we'll go sine of 45, and we'll hit equals. You should get something like 0.7071, etc., etc., etc. What is 0.71? It might even be a third root 2 over 2, something like that you might get. But if you hit the S to D button or turn it into decimal, you should get 0.7071. And we'll plot that there. If I do sine 90, the same thing, hit equals, we'll get 1. We'll plot that. Continue on and do this for yourself if you want for sine 135, sine 180, and even for sine minus 45, minus 90, minus 135, minus 180. And you should get your values to look like this. Okay, we can join those together using a nice curved line, and it'll look like that. And that's part of the sine graph, because obviously we can go higher than 180, we can go lower than minus 180. But we get this, what we call a sine wave shape, or sinusoidal wave, and that's what the sine graph looks like. Can you spot any patterns? Well, you mightn't have just yet, but if I do expand it out beyond the minus 180 and the plus 180, you'll see, maybe see some patterns that you might have seen before. So this is an expanded version of the sine graph. Like I said, what patterns can you see? You can pause the video. Unpause it. I'm going to take you through some now. So I'm going to take you through. It repeats every 360 degrees. And what I mean by that is, if I take this section here from 0 to 360, it goes up, down, and up. And I move that back to show the 360 degrees before it. You'll see that that's exactly the same as the one to the right. You'll see that it cuts at 0, 0, so it goes through 0, 0, there. And it cuts at every 180 degrees before and after. So at plus 180, plus 360, plus 540, minus 180, minus 360, minus 440, etc., etc. Sorry, one more thing to point out about this. I should say the maximum value is 1 and the minimum value is minus 1. So the biggest value you can have for sine is 1 and the minimum value you can have for sine is minus 1. If we do the same for the cos graph, this is what the cos graph looks like, and it looks very, very similar. Any patterns to be spotted here? Well, it repeats every 360 degrees again, though not in exactly the same way, but I'll give you this 360 degrees here between minus 180 and plus 180, and I can move that to the left, and sure enough, it's exactly the same shape. That hump, if you want. You could think of these all as camel's humps. It's symmetrical about 0 degrees, so it doesn't go through 0, 0, but it's symmetrical. So when I go this side of the graph, it's the same as if I go this side of the thing, and there's a line of symmetry or a reflection line there. It cuts first at 90 and minus 90, and at every 180 degrees before and after, just like before. So if you can get yourself started on the sketches, you can usually continue them on, because there are patterns in them. You're going to be, I'm going to get you to sketch these graphs a lot, so we get to do them again and again and again and again. So let us use this knowledge and see if we can solve some more trigonometric equations. So we're going to solve equations involving sine, cos, and tan with more than one solution. Sketching graphs should become second nature. Again, it seems unlikely when you start this topic, and many people use the cast diagram as another alternative for this, but I find that it doesn't give as much understanding of what you're doing. So with that in mind, I'm going to keep you through this, and from teaching people before, people do get very au fait with sketching what the sine and the cos graph looks like. It does become second nature. So the example we're going to do, we're going to solve sine x for 0.5, as we did before with sine theta, but I've turned this to sine x. And you'll notice on the right we have an extra bit that says, in the range, x is between 0 and 360. So I want all the solutions that lie between 0 and 360 degrees. The first step's just like before. We need to find what's known as the primary solution, and we'll do this by doing the inverse sine of the 0.5 or the sine of the minus 1. We need a starting point. We got that earlier on to be 30 degrees, and you should get 30 degrees again here. This should be familiar if you mastered the last lesson, like I said. Let's look at this in the graph. So if I show you the part of the sine graph that I'm going to talk about, so between 0 and 360 degrees, I'm going to add a line where x is equal to 0.5 or the value is equal to 0.5. So if that's 0, that's 1. I'm going to put a line roughly halfway between them, and that would be the line that would where the value is equal to 0.5. So I'm looking for the angles at which sine of x, which is this graph, is equal to 0.5. And you can see the points where it cuts the line. There's a solution at every point that cuts this line in the graph. So our primary solution is found here, and it's usually the first positive one after 0 on your calculator. There. And one of the reasons that I like you sketching the graph is that you can see that where that sketch, or that line appears between 0 and 90, well, that 30 degrees seems reasonable. And you can get your solution and go, that makes sense to me. Our range of solutions are put between 0 and 360, so we're looking all the times that it cuts the line after that. You can also see that there would be a solution here. So that line cuts there. This one to the right falls outside our range, and therefore we don't need to worry about it. Okay? But how can we find the value of that second solution? So I'm going to blow it up a little bit like this. I'm going to put my line for 0.5 there. And I'm going to put my primary solution in there. That distance between there and there is 30 degrees. And because of the way the sine graph works, and even the cos graph and the tan graph to a certain extent as well, they're very symmetrical, they're very repeating patterns, they're very much the same thing happening over and over again. Because these things kind of have this symmetry, we can say that if that's 30 degrees, then this gap here must also be 30 degrees. And if we want to know what the value is of where that cuts, we do 180 work from there, take away our 30, and that gives our second solution to be 150 degrees. So our solutions for the sine x equals 0.5 between 0 and 360 is 30 and 150, and they are all the solutions that there are. So like I said before, sometimes where you in GCSE would have solved for one solution, there can be multiple solutions, and this is one of the things we're going to look at in more depth. So let's try another example. This one quite fresh. So cos x is equal to minus 0.23, and we're going to do it in the range from minus 270 to plus 270. Okay, primary solution just like before. We're going to do inverse cos of minus 0.23, and we should get 103.3. When we sketch our cosine graph, like so, and go put in a line from minus 0.23, well there's not, there's minus 1, minus 0.23 is going to be roughly there. We can see that when we put in our primary solution at all the places that it cuts, you can see that 103.3 seems reasonable. That's 90, that's 180, that's about right. Where else do we get solutions? In this, I've only put up the range here. You get one here, here, and here. So we have 4 solutions altogether. It's quite straightforward to find out the next solution to the left, because as we said about the cos graph, it's completely symmetrical about the centre. So if that's plus 103.3, then this one, by symmetry, to all across this line must be minus 103.3. The other two are a little bit more difficult. So if we look at the gap between the cos x equals 0, so here, at 90 degrees, we work out the gap in the primary solution. So this gap in here, if I mark it a little bit, this gap in here is then 103.3 minus 90, which is 13.3. So this gap in here must also be 13.3. And once we take that on, that'll be a 270 minus 13.3, which is 256.7. And if I do the same thing on the other side, by symmetry, look at the other one must be minus 256.7. And there are our 4 solutions. In the range minus 270 to plus 270, do 103.3, minus 103.3, 256.7, and minus 256.7, all to 2 decimal places. Okay, so that's the general idea. Let's look at the tan graph, because it's slightly different. This is what the tan graph here looks like, and you see that if you were just looking at the sine and the cos graph, you're going, oh my god, it's like a monstrosity compared to it. But again, it has patterns. It repeats every 180 degrees. So if I take this section between minus 90 and plus 90, you see this wave here, it repeats, and it's exactly the same as the one just to the left of it. So instead of 360 degrees for the sine and cos, you've got 180 for these, and it cuts at 0, 0. The other thing to point out, the points where it disappears, the lines where it disappears kind of goes disappearing off down in the top, goes disappearing off up the top and down the bottom. They're called asymptotes, and in yellow, and they will never actually touch those lines, but you should do tan of 80, do tan of 85, do tan of 89 even, and you think, god, the numbers don't get that big. Do tan of 89.9 or 99 even, and you'll see that the numbers get really big very quickly, but it never actually reaches, because when you do tan of 90 or plot your tan of 90, it'll come up error on your computer, and that's because there is no value that goes for tan of 90. Do the same for minus 89.9, you'll see a very small number there as well. Tan, as long as you get that it cuts at 0, 0, and minus 90 and plus 90 are the asymptotes, then it just repeats every 180 degrees thereafter. It becomes very easy, and it becomes quite easy to calculate as well. So solving equations involving sine with more solutions, we're going to look at an example where we must change the range. So what we're going to do ones for k theta or something for more than 1 theta. So we're going to do tan 2 theta equals minus 1.32, where theta lies between minus 80 and plus 180. And there are a couple of ways to do this. Now I'm going to encourage you to do one, but I'll show you why we'll do this. If you're comfortable with how graph transformations work, we'll know that tan of some number theta means that we divide the interval along the x-axis by k. For instance, the graph of tan 2 theta has period of 90 instead of 180. So instead of repeating every 180 degrees, it'll be half of that, it'll be 90. So our method 1 is that we change the graph, and a graph of tan 2 theta would look like this. We can get a primary solution just like before and pick up and plot the solutions in the graph in that range before simplifying, and we'll see it carried out shortly. The more popular method that we use is to use the one version of the trig graph that you already know. Okay, so you only have to remember one sine graph, cos graph, and tan graph. So we're going to adjust the range to start off with. So if the range is minus 080 to plus 180 for 1 theta, then to get 2 theta, one must multiply our range by 2. So it becomes between minus 360 and plus 360. So the solution will then look as follows. We get our primary solution by doing our tan to the minus 1 of 1.23, and we'll get our value for 2 theta. When we do that, we'll get 2 theta equals 50.89. How many more solutions are there in our range? Well, if we short part of the tan graph that's relevant, we sketched it. I've put in a line for 1.23 here. To do from minus 360 to plus 360, you'll see that we have a solution there, and we also have another 3 solutions there and there. There and there. Okay, they're all the ones that fall inside our range. So if I take those ideas, and I've got my adjusted range here at the bottom, no matter which method you use for finding the solutions, you should get 4 solutions in total. For method 2, since the tan graph repeats every 180, we'll just have to add and subtract 180 degrees until our answers fall outside the range. So if I take the 50.89 and add 180 once, I get 230.89. If I add another 180, I get 410.89. If I have 50.89, which is this one here, and I take away 180, I get minus 129.11. Take away another 180, get minus 309.11. Take away another 180, get minus 489.11. And then decide which ones are between minus 360 and plus 360. Well, that one is. Minus 129.11 is. Minus 309.11 is. But both the 410 and the minus 489 are not. So our other 3 solutions are 230.89, minus 129.11, and minus 309.11. Now that's solved for 2 theta. We want to solve for theta in our problem. So to get what 1 theta is, we'll divide each of our answers by 2. And we get 25.45, 115.45, minus 64.56, and minus 154.56, all the 2 decimal places. If you want to go through that example again, you can, but the general idea is you do it just like before, except you change your range, depending on whether it's 2 theta or 3 theta. If it was 3 theta, it would multiply your range by 3. If it's 2 theta, multiply by 2. You solve and get your solutions just like before, marking them on your graph, etc. And then to get the bit at the end, when it's more than 1 theta, you just divide by whatever the number is in front of the theta to get your answers. For method 1, since the tan 2 theta graph repeats every 90 degrees, we'll solve our primary solution and then add and subtract 90 degrees. So this is only if you're really comfortable to find between finding you're using your transformation of graphs. So primary solution is 2 theta equals 50.89. Divide by 2 to find theta, it gives us 25.45 as a primary solution. If we add and subtract 90 degrees, we get our 4 solutions to be 25.45, etc., etc. I don't suggest that you do it that way, but that is how you do it, with changing the graph rather than the range. Just like before. Most prefer method 2 where they change the range, but understanding what happens with the transform graph can be just important, and it can help inform what you do when you transform a graph. And they're using the little Desmos plot, you can see it on there. So 1.23, no matter what way I do it, I get those values to check. Okay. So the steps, I thought I'd take you through each of the steps for each problem. Never the way you'd want people to do it, but certainly if you're trying to follow along at the start, having steps to follow along till the point where it becomes a more natural process and a more natural thought process is good. So, first thing to do, identify your primary solution. So do your sine of the minus 1 or inverse cos or inverse tan or whatever. And then change your range as appropriate. So if it's only 1 theta, you don't need to worry about part 2, change the range of the graph. But if it's 2 theta or 3 theta, you should change your bit. Sketch your appropriate graph either the sine, cos, or tan, and check for multiple solutions using your symmetry. Use the properties of the graph to find all solutions, and that would be the way you do it. Okay, so next time, that's just kind of finished for that what I teach in the course. I'm going to start on some revision. I've got some revision exercises, and we can certainly work through these in class if you're with me, or I'm just going to work through a couple that I've got here. Our objectives were to draw trigonometric graphs for sine, cos, and tan. Hopefully we've done that, and solve equations involving sine, cos, and tan with more than one solution, possibly, for 1 theta and for more than 1 theta as well. We've done those. Practice, practice, practice. For exercises, solutions, quizzes, and downloads around this subject, go to flipmath.co.uk and search for trigonometry. Feedback on all resources should be sent to @flipmath or in the comments to this video. Thank you for watching, and I'll catch you next time.